All right, welcome back, everybody. We're here to wrap up chapter 2. And to wrap up chapter 2, we're going to be talking about resonance the whole time. So you may recall that when you solved Lewis structures in the past, this must have been in General Chemistry 1 for you. Sometimes when you solved a Lewis structure for a molecule, there were actually two valid structures. And this was introduced to you as a form of resonance. So back then, probably what you had to do, you solve the multiple structures and then pick the best one. We're going to do something similar here, but the thing is, resonance is so common in organic chemistry that really we want to be able to recognize resonance just by looking at a molecule right away. So we're going to try to boil it down to about 5 patterns that you're going to see, some more often than others. There's a couple that are extremely common, and then some that you don't see very often. But yeah, so let's go ahead and talk about resonance here in the context of organic chemistry. So yeah, so the reason that resonance is so common in organic chemistry is because pi bonds can be spread out on from a set of atoms that are in a pi bond to a neighboring atom that has an empty p orbital, or one that actually has a lone pair in its p orbital. These are examples of ways that the atoms can share electron density and give you different resonance structures. So, for example, if you look at what we call the allyl carbocation, don't worry too much about this. This is kind of like an old word. We're going to be using this a lot, allyl. But the idea here is basically we have 2 positions that are in the double bond, and then we have a neighboring carbon position that's right next to the double bond. This is what we call the allylic position. That's why we call it an allylic carbocation. So because there's an empty p orbital on carbon 3, that can actually share electron density. It's in the same plane as this pi bond here, as we're about to see on the next page. So here, carbon 1 and 2 were participating in a pi bond in the Lewis structure we just showed you. And then carbon 3 had an empty p orbital. Well, that empty p orbital can align itself such that it overlaps as well, and thus share the electron density. And that's something that, again, just always go back to, why do electrons behave the way that they do? They behave the way that they do because they want to lower their potential energy. And the more they get spread out over the more atoms, the lower their potential energy is going to be. The reason that an electron, or 2 electrons in this case, would kind of spread themselves over 3 atoms is because rather than just interacting with 2 positively charged nuclei, now it can actually interact with 3 positively charged nuclei. So this forms your bonding molecular orbital. This is one of many reasons that molecular orbitals can look much more complicated than what we would simply draw up from a sigma bond or a pi bond. So because these are 3 atomic orbitals that contribute into a bonding orbital, if you'll recall from chapter 1 when we talked about molecular orbital theory, we said that when 2 atomic orbitals combine, they form a bonding and anti-bonding orbital. So they form 2 orbitals, conservation of energy. Similarly, when you have 3 atomic orbitals combined, you form 3 new molecular orbitals. You get the bonding molecular orbital. That's the one that I've described already, where the electron density is smeared over the 3 atoms in such a way when they're aligned like that. There's also a non-bonding molecular orbital. This non-bonding molecular orbital does not involve the second carbon and only involves the terminal carbons, so carbon 1 and carbon 3, with opposite p orbitals orientations. And then finally, you have anti-bonding molecular orbital, which is where the p orbitals, rather than being aligned like in the bonding, are opposite. So they are not aligned at all, and so you get these nodes in between them. The new thing here is the non-bonding molecular orbital. So because this allyl carbocation has a charge of +1, it's going to have a full bonding molecular orbital. It has 2 electrons, right? Think of the number of pi electrons. It's got 2 pi electrons. Here, I can go back and show you. Those are the 2 electrons that are involved in the pi bond. There's no other, this is an empty p orbital here. There's only those 2. So then in molecular orbital theory terms, you fill the bonding molecular orbital, and then you have 0 electrons in the non-bonding and 0 electrons in the anti-bonding. quick review, that means that this orbital is the highest occupied molecular orbital, and the non-bonding molecular orbital then is the lowest unoccupied molecular orbital. So HOMO down here and LUMO up here. Now, looking at the non-bonding molecular orbital, it seems like if this is missing an electron, in other words, that's where the positive charge is, the positive charge we would predict would be spread to the carbon 1 and carbon 3. And in fact, that's what we find if we look at the possible resonance structures. We can imagine a resonance structure that has a double bond between carbon 1 and carbon 2, and then an empty p orbital on carbon 3. Or similarly, we could have an empty p orbital on carbon 1, and then a pi bond between carbons 2 and carbon 3. So these are both examples of possible resonance structures. Now, keep in mind when you draw resonance structures, as a brief review, the way that you draw them is you draw the bond line structure in this case. You could draw the Lewis structure or whichever structure you want. And then that is separated from the neighboring structure here by a resonance arrow, which is just a two-sided arrow. So going either direction. Then what you do is you put the whole thing in brackets. And we're going to show that because we want to represent that these aren't different species. These are kind of the same species, different ways to describe the same species. We know that overall, when we actually have these two resonance contributors, the real structure is somewhere in between the two. In this case, both are equally valid. We'll talk about validity here later on. Since both of these contributors can contribute, when we mix them together, we get a 50-50 mix where rather than having a pi bond between carbons 1 and carbon 2, or between carbon 2 and carbon 3, instead, those pi electrons are spread out entirely between carbon 1 to carbon 2 and carbon 2 to carbon 3. So it's like we have, rather than a double bond, we have a 1.5 bond here and a 1.5 bond here. Also, the positive charge is spread out as well. Rather than being located just on carbon 3 or just on carbon 1, it's actually partially positive on both of them. Again, the way that you want to think about this is that these aren't switching back and forth. In fact, the electrons just occupy the bonding molecular orbital. They're just there, or in the case of the non-bonding molecular orbital, they're not there. So yeah, so the analogy here, this is a good analogy, a fruit analogy. The nectarine is half peach and half plum. Actually, I'm not sure about that. I'm going to look that up. I thought a nectarine was just a peach, but this is something that can happen. Oh, how about this? A pluot, okay? You go to the grocery store, there's these little pluots. There's half plum, half apricot. And the way that you get those is you breed an apricot with a plum. It's not like it's half plum, half apricot, like switching back and forth. It's just a pluot the whole time. It's half and half all the time, if that makes sense. Anyways. Okay, so I already mentioned this here, but the more delocalized your electrons are, they're spread out over more nuclei. That is a stabilizing interaction, and so that's going to actually stabilize the overall molecule. So yeah, so if it spans a greater distance, there's actually more space for the electrons to exist in, so they're not going to interact with each other, they're not going to repel each other, and again, there's more nuclei to kind of hold them there. Yeah, so we see delocalization of electrons and delocalization of charge. Oh, and the reason is the stronger the charge is, the less stable it's going to be. If you had a fully positive charge, that's going to pull on electrons more and more and try to get filled back up. But here you have a half positive charge on both of these carbons. So it's not as intense. It's not pulling as hard on any electrons around it. Okay, now here's the new thing that we really want to make sure that we understand. And this is something that you're going to want to practice a lot, which is the curved arrows. So this is classic organic chemistry. We're going to be using this from today until the end of next semester. And so, eventually you'll see these kind of dancing around in your head, I'm sure. But the idea is what we're going to do is we're going to show electron movement by using what we call curved arrows. So we have the tail of the arrow here and the head of the arrow here. Just keep in mind, the tail is like where the arrow comes from and the head is where the arrow points to. Keep in mind, the tail is going to be where the electrons are currently located, and the arrow is going to point to where the electrons are going to end up. So just to keep in mind here, this is an example of a curved arrow. Here, we're starting from this pi bond here, right? So this pi bond here points to now this bond over here. So what's going to happen is these two pi electrons are going to move over, and they're going to be, rather than between carbon 1 and carbon 2, they'll be between carbon 2 and carbon 3. So it's kind of pointing, oh, it's going from here to here. Again, this is something that you may as well just practice now. I recommend, again, using your book. We have the sample exercise packet as well that I'll be walking you through later, and that you can start working on whenever you feel like you've got this down. But this is something that if you can't do this, you're going to fail the class. So definitely make sure that you understand how to do this. Okay, so we've got some rules for curved arrows. We're just going to go through these rules here. And these are in particular curved arrows for resonance. So keep in mind, like these are like resonance rules. In the future, we have reaction rules, and that's more like no holds barred. So just keep in mind, this is just to make sure that you're not screwing up the resonance part. Don't let this mess you up in the future with reactions, because with reactions, sometimes this won't go. So for example, okay, so rule number 1, never show a sigma bond as being delocalized. Sigma bonds can't be delocalized. It's got to be the pi overlap that drives the delocalization. So for example, here it's showing this sigma bond forming a pi bond over here. That's not delocalization. That's a reaction that's occurring. So that's different. That would be like if you had a reaction that occurred, but this is your reactant, this is your product. That's not what we're talking about. We're talking about resonance, right? These have to be valid descriptions of the same molecule. And here we have a carbocation on a pentane, and here we have like an alkene and another carbocation, an ethane carbocation. Totally different. This does not, no good. Yeah, so again, single bonds break in a chemical reaction, which we'll learn later on. And resonance is only going to exist for electrons in overlapping p orbitals. So pi bonds, lone pairs, and empty p orbitals. Okay, rule number 2, the octet rule. Don't exceed an octet for the second row elements. So the ones that you're going to see the most are boron, carbon, nitrogen, oxygen, and fluorine. Just don't exceed 8 electrons. The maximum number of electrons that a second row element can have is 8 electrons. It cannot dip into its d orbitals to extend past that, so just keep that in mind. Like here, for example, this is showing oxygen forming a pi bond with carbon, but that carbon already has 1, 2, 3, 4 bonds. That would give that carbon 5 bonds, 10 electrons. That exceeds the octet. Same thing here, because nitrogen has a lone pair, so 2, 4, 6, 8 in its octet. Trying to give it 2 more, again, gives it 10. So just keep that in mind. Don't break the octet rule for second row elements. Now, third row and up, you know, the rules are off because those can hybridize with their d orbitals. But for carbon, that's the most important one. Oxygen, nitrogen, can't do that. Keep in mind, sometimes these second row elements, especially boron and carbon, will have less than an octet, but they won't have more than an octet. So this is something that we'll see as like a carbocation here. This is one possible pattern that we're going to see. If you have a carbon double bonded to a more electronegative atom, there's a resonance structure that exists where the pi bond is assigned entirely to the more electronegative atom. Again, one of the patterns that we'll see by the end of the chapter. And here we have a positive formal charge on the carbon, and it's only got 3 bonds. It's got 6 electrons in its octet. That is lower than the octet rule, right? But it's okay. That's not against the law, against the rule. It's not ideal, but it's okay. So yeah, so we always want to make sure that when we draw resonance structures, we also draw out the formal charges. So just keep in mind, like that's what we were doing in the last lecture. We were talking about how do you recognize what the formal charge is on each molecule. So let's go ahead and do that with this one here. So I'll walk you through it. I'm gonna take a minute. You can pause the video and try to write the answer down, and then we'll go over the answer together and try to, we'll show what the answer should be. So here, so what we're doing is we've got this molecule, we've got an oxygen, it's got 2 lone pairs, and then it's bonded to 1, 2 other things, so no formal charges. Then it's bonded to a carbon that's in a pi bond with another carbon. So what's going to happen is this lone pair is going to form a pi bond between this oxygen and this carbon. Now that would violate the octet rule for this carbon, but at the exact same time, this pi bond that it's in is going to break, and these 2 electrons are going to be assigned to this carbon here. Okay, give it a try. Figure out what the structure is going to look like when you're done. I'll give you, go ahead, pause the video. Okay, I hope you took the time to pause the video, and now let's go ahead and take a look. If you follow it, what happens is you form a carbon-oxygen double bond, like I said. You broke the carbon-carbon double bond, and now those lone pairs are here. But now let's go ahead and evaluate. Well, we have an oxygen that has 1 lone pair and 1, 2, 3 bonds. But oxygen is divalent. So having a trivalent oxygen means that this is going to have a positive formal charge. On the other hand, down here, now we have a carbon that has 1, 2, and then there was a 3rd hydrogen bonded here. And it has a lone pair. So this is a carbanion with a lone pair assigned to it. That gives it 1, 2, 3, 4, and then a 5th electron from its carbon-hydrogen bond. 5 electrons is 1 more than carbon should have. Carbon should have 4 valence electrons. That means it's got a negative charge. It's a carbanion. So this is an example of a carbanion here. So go ahead. This is, again, in the book, you're following along Skill Builder 2.7. And then there's also a little section called Practice the Skill 2.15 and 2.16. Just kind of like following the resonance structures that they give you. You also have this sample exercise packet that, again, I'll do later on. Okay, now I mentioned earlier that because this is something that comes up all the time, resonance structures, we actually boiled it down to just 5 patterns for organic chemistry. And so I'm gonna name them here, and then we're gonna go through the individual cases here. We just wanna be able to recognize them when we see them because, again, this is gonna be something that from literally now until the end of Organic Chemistry 2, you're gonna need to recognize these 5 patterns whenever they show up. So the more you can like bake it into your brain, the better off you're gonna be. Okay, so the names are, and again, we're gonna go through each of these individually. We don't need to list these or anything like that. We have the allylic lone pair, the allylic carbocation. We have a lone pair of electrons adjacent to a carbocation. We have a pi bond between 2 atoms with different electronegativities. And finally, we have conjugated pi bonds in a ring. Again, I just want to emphasize the only way that you're going to get this is you have to do lots of practice. So just be aware of that, do the homework, do the sample exercises, and then also walk through your book. Your book has really good examples of these to work from. Okay, so real quick, I know I briefly mentioned the allylic position before. There's another name that we're going to use, which is vinylic position as well. So anytime we have a pi bond, the atoms that participate in a pi bond are what we call the vinylic atoms. Here, this is in this case, it's carbon 2 and carbon 3. They're involved in a pi bond. They are the vinylic carbons. Now, that's okay, that's relevant. That occasionally comes up, but what's actually more important to be able to recognize is the allylic positions. So the allylic positions are any carbons or basically any atoms that are bonded to the vinylic positions here. So the way that this is structured is you actually have 1, 2, 3, 4 different carbons all in the allylic position. That's kind of the maximum number you could have from this here. The reason that we do that is because when we find these allylic lone pairs are delocalized by resonance through a pattern I'm about to show you. So like looking here, this nitrogen has a lone pair, but it's not neighboring any pi bonds. This pi bond is 1, 2 positions away. This is the vinylic position for that. I'm sorry, this is the vinylic position. This is the allylic position. So this is nothing over here. On the other hand, this down here, this is a vinylic carbon, and it's neighboring an allylic nitrogen. So this lone pair is allylic, and it will have resonance, as we're about to see. So again, be able to recognize vinyl position versus allyl position. Once again, I just want to re-emphasize, this is something you're going to have to do until the end of Organic Chemistry 2, and perhaps beyond, you know, like maybe you're going to really love chemistry and you know, join our cult. But even if not, you just got to get it through the end of the year. So the more practice you get on this now, the better off you're going to be. Okay, so these lone pairs are allylic up here. So we look here, we have a pi bond next to a carbanion. a pi bond next to an oxygen. And here we actually have a carbon double bonded to an oxygen. That's a carbonyl bonded to another oxygen. Well, guess what? If you can you recognize what this is? It's an ester, right? Carbon double bond oxygen bonded to an oxygen bonded to a carbon. Here we have a carbon double bonded to a nitrogen. That's our pi bond. So that's a pi bond, vinyl positions, and then allylic position here. So allylic. And then finally, carbon oxygen again, another pi bond, a nitrogen in an allylic position. Each of these are allylic. So because they're in an allylic position, they actually have resonance. Now, in order to show this resonance, you have to use two curved arrows to show the delocalization. So let's start from the left here and just look at the carbanion first and make sure that we understand what's going on. So for this resonance structure, the first thing that happens is the lone pair, the allylic lone pair, is going to form a new pi bond between the carbon that it's on and then the vinyl, the earlier vinyl carbon here. At the same time that that happens, because if that was the only thing that happened, that would now violate the octet rule for this carbon. So that can't be the only thing that happens. At the same time that happens, this pi bond has to break, and the two pi electrons end up being localized entirely on this atom here. So if we're trying to follow along, what's that going to look like? Well, let's go ahead and draw it out. So again, resonance arrow, and you want to bracket it. Ooh, that's a bad bracket. I'll try one more time here. There we go, good enough. And then, so what happened is we formed a pi bond from carbon 2 to carbon 3. Good enough. And then that broke the pi bond. Ooh, that broke the pi bond between carbon 1 and carbon 2. And then this, what was the pi bond, these two electrons are now assigned solely to carbon 1. Okay, so just like that. Now, of course, wrap it up. We want to make sure we assign our formal charges. This lone pair is on a carbon. It's a carbanion, got a negative formal charge, and then we just bracket it up and we're good to go. Okay, so we can kind of follow it through for each of these, but these all follow the same pattern where here, again, we have a lone pair on an oxygen in this case. This is a allylic position because it's next to a carbon-carbon double bond. This lone pair is going to form a new carbon-oxygen double bond, and the carbon-carbon pi bond electrons, those are going to be assigned to this carbon over here. So we end up with a negative charge carbanion over here, and then a carbon-oxygen double bond over here. Similar thing happens here where, okay, so now we have our pi bond over here, and this oxygen is in the allylic position. So its lone pair is going to form a new carbon-oxygen double bond. At the same time, this pi bond has to break. This pi bond electrons are going to be assigned to this oxygen up here, et cetera, et cetera, et cetera. Okay, so let's go ahead and clear these out. Again, the more practice you do, the better off you're going to be. Okay. So one thing that we want to note is whenever you have an atom that has a negative charge, the negative charge would be delocalized, just like what we saw with the allylic carbocation before, where we had the positive charge on carbons 1 and 3. In this case, just in the same way as what we did before, we have a negative charge here on carbon 3. Its resonance structure, we have the negative charge on carbon 1. So the negative charge is like split between carbons 1 and carbon 3, so it's delocalized. Similarly here, in the second one, we start with a carbanion, you end up with a negatively charged, negative formal charged nitrogen. So there, the negative charge is split between the nitrogen and the carbon. Yeah, so kind of like finishing things up here, if your allylic atom is neutral, it's going to become positive because it's going to basically form one more bond. Like here, we have an oxygen that's already bonded twice with a lone pair. So it forms a new pi bond. That's now 3 bonds. We know that an oxygen with 3 bonds has a positive formal charge. And then whatever received the electron becomes negative. Overall, the net formal charge is going to be the same. Here it's 0 and 0, 0 and 0, and here it's -1, -1, -1, -1. So there you go. Okay, so that's allylic carbanions. Again, we're kind of following along the conceptual checkpoints. We're also going to have a big sample exercise on this as well. Next up, we have allylic carbocations. So we just want to show, for this one, it's very similar to what we did at the beginning when I was talking to you about resonance. The only difference is now I'm actually going to show you what this arrow is going to look like, and it looks just like this. You only need this one curved arrow to show it because the pi electrons in the pi bond are swinging over into an empty p orbital. There's no violation of octet rule that would occur just swinging this one over. Now, an allylic carbocation sometimes can be doubly allylic. So it can be like conjugated in a longer chain. So for example here we have a carbocation and it's neighboring a vinyl position. So it's an allylic carbocation. So we know that these pi electrons can swing over and they can form a new pi bond here, and that forms a carbocation here. That gives us our middle structure. Well, now all of a sudden, this middle structure is also in an allylic position, not just from the original pi bond, but also there was another pi bond here. It's in an allylic position from there. Now this pi bond can swing over as well. Again, we start the arrow from the pi electrons, and we point it to this new pi bond that we're going to form. Okay, and that gives us this here. So it's possible to have more than one resonance structure, especially with allylic carbocations when they're conjugated in this way. And just keep in mind, when we form our resonance hybrid, now we have partial positive charges on carbons 1, 3, and 5. Again, go ahead, get some more practice with this. This is a good time to start looking at the homework as well. But we're almost home free. These are the two trickiest ones, are the carbanion and carbocation, and perhaps the resonance thing. But we talk more about the resonance thing in organic chemistry too. So don't worry too much about that one yet. Okay, next up, easy enough. If you have a lone pair that's adjacent to a carbocation, that lone pair can form a pi bond to the carbocation. All you have to do is you draw a curved arrow pointing from the lone pair to the sigma bond between that atom and the carbocation. So you're forming a pi bond, basically. You take the lone pair, it forms a pi bond. The same thing can happen down here. This is an ether. This is like a diethyl ether cation. Here, the carbocation is neighboring an oxygen that has a lone pair. So this oxygen has a lone pair to give. So that lone pair forms a new pi bond. We get this carbon-oxygen double bond here. Evaluating the formal charges here, this oxygen now, one lone pair, 3 bonds. That means it's going to be a positive formal charge. Also, always make sure that your structures have equivalent formal charge when you add everything together, right? Here we have a negative and a positive, so total 0. And then here, everything's 0, so 0. Here it's +1, so +1. And then over here, +1, +1. It checks out. Easy enough, right? Okay, next up, if you have a pi bond between atoms of different electronegativity, you can basically do the reverse of what we just showed you. So we start from a carbonyl here. This is a carbon that's pi bonded to oxygen. Now, oxygen is more electronegative than carbon, so we already know that it's holding on those bonding electrons really hard. And what can happen, and this is another way that you can describe this molecule, is we can basically assign these pi electrons to that oxygen. And we get this valid resonance structure. Now, is it the best resonance structure? No, I mean, this only has 6 electrons in its octet. This one has a full octet, but it's a valid resonance structure. It can exist. So this is another one that we have to keep in mind. And again, this can only happen if you have 2 atoms of different electronegativity. But it happens a lot in organic chemistry because you see carbon double bonded oxygen, carbon double bonded nitrogen, that kind of thing. Okay, the last one, conjugated pi bonds in a ring. Again, this is something that you're going to recognize here. This is a special ring that we're going to call the benzene ring. The benzene ring is basically a 6-membered ring that has alternating double bonds. So it's like single bond, double bond, single bond, double bond, single bond, double bond. And those alternating double bonds can just kind of like flip positions. So we go from a double bond between carbons 1 and 2 to now it's being between 6 and 1. It was between 5 and 6, and now it's going to be between 4 and 5. And then now here it was between 3 and 4, and now it's between 2 and 3. So that's just like another way that this can kind of go around in a ring, and just another pattern that we have to recognize. This is going to become, again, very important in organic chemistry too, but for now, it's just not that relevant. We just want to be able to recognize it. Okay, so there's our 5 patterns. Got to be able to recognize them and name them when it comes to it. Okay, so you can practice with this one here. I'm gonna go ahead and give you a shot. So I'll try to like point out some of the names. I recommend go ahead, pause the video, try to recognize the different patterns that can exist on this one. And I'll just like walk you through it afterwards. So again, go ahead, hit pause, recognize those patterns, and we'll pick it up. Okay, I hope you hit pause. Anyways, let's go ahead and take a look through the patterns here and see what we can see. And I'll go ahead and start drawing some of the arrows here as well so that we kind of get ready for that practice. Okay, so like looking here real quick, let's look and see. So there's a few different ones that I see. In fact, let's just start from the top. Let's see, do we see any allylic carbanions or allylic lone pairs, excuse me. So let's go ahead and take a look. So we've got 2 different double bonds. We have a double bond here, allylic position here and here, no lone pairs. Another double bond here, allylic position here, carbocation, we'll come to that in a second, neutral, neutral, and oh, lone pairs on this oxygen. So that's an allylic position with a lone pair. That means that we can draw the allylic lone pair resonance. So if we recall, that's where this lone pair is going to form a new pi bond from carbon to oxygen. And then this pi bond is going to form a lone pair on the far neighbor in the vinyl position. So we form a new carbon-oxygen pi bond, and we form a carbanion right here. You can draw that later. I'll put that, you know what, I'll put that in the sample exercise packet as well, just to kind of like point out the different ones. The next one would be allylic carbocations. Here we have a carbocation, and it's in an allylic position from here. So we know that we can actually switch this over by pointing from the pi bond to like if we call this carbon 1, 2, 3, it's flipping from between carbon 2 and 3 to be between carbon 1 and 2. And when we do that, we know that that structure is going to have a positive charge on this one here. Okay, next up, do we have a carbocation next to a lone pair? We only have one carbocation, and sure enough, it's next to a lone pair. So we know we can actually form a carbon-nitrogen pi bond in this case. So that carbon-nitrogen pi bond could form, and that would give us a positive thermal charge on this nitrogen. Next up, do we have carbon double bonded to a more electronegative atom, or a double bond between atoms of different electronegativity? This is carbon and carbon, so not there. But here we have a carbon-nitrogen pi bond. So we know that the carbon-nitrogen pi bond, we can actually draw that as a resonance structure. We take the pi electrons in the bond and assign it as a lone pair to the nitrogen. So it's going to give us a negative formal charge on this nitrogen, a positive formal charge on this one here. The last pattern would be aromatic, but we don't see a benzene ring. Again, we would look specifically for a 6-membered ring that has 3 alternating double bonds. So just keep that in mind. Okay, that's some fun practice. Again, get used to it. Okay, so real quick, this is going to be a review from what you talked about with Lewis structures, but I know that's been a while, so remember. So this is going to be kind of like a review of how we know what's a good resonance structure, or what's a better resonance structure. So if we have multiple resonance structures that all contribute to the hybrid, sometimes this hybrid will be an even mix of the two if they're equally valid, but oftentimes some resonance structures will be more important in the resonance hybrid. They're just more likely, or they're more stable. So we're going to go through the rules that help us do this. It's all about like the formal charges and the way the formal charges are listed. And then once we kind of figure out like which one is the best for the individual rules, we can identify what the major contributor to the hybrid structure is going to be. Okay, so first up, the rule number 1, the most significant structure is going to have the greatest number of filled octets. So rule number 1 is basically the octet rule. So here we have a resonance structure where we have a lone pair next to a carbocation. So again, this one violates the octet rule. So we have an unfilled octet here. When we form its resonance structure where we form an oxygen-carbon pi bond, that gives a positive formal charge to the oxygen, but it fills the carbon's octet. The oxygen still has a filled octet, every atom here has its filled octet. Since this structure has filled octets, it's the major contributor, and the resonance form is going to look more like this, or the resonance hybrid, excuse me, is going to look more like this than it does like this. Okay, so that's number one, octet rule. Number two, the one that has the fewest formal charges is the most significant. So going here, what we have is we have a carbon that's double bonded to a nitrogen one way and single bonded to a nitrogen another way. And this nitrogen is NH and this is NH2 up here. So this is a trivalent nitrogen, neutral. Trivalent nitrogen, neutral. Well, we just formed tetravalent nitrogen, which has a positive formal charge. Sorry, the charges didn't go in my slide here when I copied this over, so sorry about that. This should be a positive here. And then this one has 2 lone pairs and 2 bonds. That's a negative thing. Okay, and then the other thing that we can do, we have a carbon bonded to a more electronegative atom, so we can draw another resonance structure where we assign the lone pair to this nitrogen. That makes this nitrogen neutral, but actually this carbon now becomes a carbocation with a positive formal charge, and then this one stays as a negative nitrogen formal charge over here. Okay, we have filled octets in the first two. So these are going to be major contributors. This is going to be a minor contributor because it has an unfilled octet. But we can actually identify the better one here because this one has 0 formal charges and this one has 2 separate formal charges. So this one's going to be the biggest contributor. This is going to be a contributor, and this is going to be a very minor contributor here. Okay. Keep in mind, like, basically what you can do now is if you have like a delocalized formal charge, you only want to draw the resonance forms that show that delocalization. Don't worry about the ones like basically don't worry about this minor contributor when you actually draw the resonance hybrid, because that's not going to have like a real effect on the formal charges. So that's what this slide is saying. Okay, rule number 3. So rule number 3 is when a structure has a negative charge on the more electronegative atom is more significant. Likewise, a positive charge being on the less electronegative atom is going to be more significant. So here, again, apologies that the charges didn't take. This is monovalent oxygen that's got a negative charge. When we see that it's an allylic lone pair, so we can do the allylic lone pair resonance, that puts a negative charge on the carbon. Well, oxygen is more electronegative than carbon, so it's more stable having the negative formal charge. So this is the better contributor here, and this is the less likely contributor over here. Now here what we have is, we have oxygen that's trivalent, that's got a positive formal charge. Okay, oops, sorry, and in this case, we have an allylic lone pair on this nitrogen. So we can imagine we do the allylic lone pair resonance structure. Hopefully we're good at that, or we need more practice, that's okay too. That puts a positive formal charge on the nitrogen. Well, oxygen is more electronegative than nitrogen, so it really doesn't want this positive charge. Nitrogen, it's a more electronegative, but not compared to oxygen. So this is going to be the major contributor in that case. Okay, so hopefully that's a little bit of review, but definitely keep working with the skill builder, and we have some of those problems in the sample exercise packet as well. Okay, yes, so here's your practice this skill. Go ahead and draw your significant resonance structures for each of them. We're going to do this in the sample exercise packet. So we'll have the answers there, but this is a good time that you can kind of like think it through and work on them. Okay, so one thing that we want to keep in mind is that the resonance hybrid is kind of like, the resonance hybrid just sort of brings all of the electrons together. So in terms of molecular orbital theory, what we want to say is that the pi electrons are going to be smeared over both resonance forms. So the resonance hybrid sort of, in this case, contributes equally. We get a 50-50 mixture. I know that's what I said before, but we want to see that this resonance hybrid is shown and validated in the molecular orbital theory. Okay, a couple more things. One thing we want to note is that we have these delocalized lone pairs. So localized electrons, that's like a local, the lone pair that's not involved in resonance. That's localized on a single atom. So you think of like water, H2O. the oxygen there has 2 lone pairs. Those are localized. They're not delocalized at all. Delocalized or lone pairs that are involved in resonance are delocalized, and they're more stable because they're smeared out over more places. So again, it's got to be, in order for a lone pair to be adjacent, it has to be, I'm sorry, for a lone pair to be delocalized, it has to be adjacent to an atom that has this unhybridized p orbital. In most cases, that's going to be with a pi bond, so a pi bond like this, or it could also be in the case of like an empty p orbital, like what we see with the carbanion or carbocation. So here, for example, what we see is, okay, so this is just kind of giving you an idea of like how you can understand if something is sp3 or sp2 hybridized. So here, what we have is we have an amide, right? So it's a carbon double bonded to an oxygen, single bonded to a nitrogen. And we know that this lone pair is delocalized because it fits the allylic position for a lone pair. Since it's delocalized, you know that you can form this structure here. Now, we would predict if we just look at this structure, this would be an sp3 lone pair, and here, this should be an sp2 nitrogen. Well, this kind of gives it away, but basically, if a lone pair is delocalized, it has to be in an unhybridized p orbital. Even though this looks like it's an sp3 hybridized nitrogen, in fact, it is sp2 hybridized because of resonance. So this lone pair has to be in an unhybridized p orbital in order to be able to participate in this resonance. And just remember, why do we hybridize at all? It's so that we can maximize bonding. Well, in this case, we can maximize bonding by keeping this electron available for resonance. So in the case where you have, like this nitrogen, this is what's called a pyridine ring. This pyridine ring has fits what we know about like a 6-membered ring with alternating pi bonds. That's resonant. But this lone pair here, actually, in this case, it has to be in an sp2 hybridized orbital. Because check it out, this nitrogen has 1, 2, 3 bonds, 2 sigma bonds, and a lone pair. That's sp2 hybridized. And then we've got the pi bond from nitrogen to carbon in this case. So this lone pair, it can't be in an unhybridized p orbital because this nitrogen's unhybridized p orbital is already taken up. That means it's actually in an sp2 hybridized orbital, so it's not involved in this situation at all. So it can't overlap. We're already using nitrogen's p orbital. So in this case, it's a localized lone pair. Just like keep that in mind. It kind of comes up every so often. Yeah, so again, that is what we mean here at the very end. We're talking about section 12 here of chapter 2. We can't assume that a lone pair is delocalized just because it's next to a pi bond. We have to also make sure that it's basically, if that atom is already participating in a pi bond, then it cannot be involved in the in like a resonance structure. Like here, this nitrogen's in an allylic position. This nitrogen technically is in an allylic position, but it's also a vinylic position. So because it's a vinylic lone pair, it cannot be delocalized. It just does not work out. And then over here, it's not even close to a pi bond, so you wouldn't even consider this one to be delocalized. It's just localized. Okay, all right. So quick review. Remember, the delocalized lone pairs versus localized lone pairs. Most of the time, an allylic position lone pair is going to be delocalized unless that atom also is involved in a pi bond, so it becomes like a vinylic position. You can think of it as like the vinylic position is more important than the allylic position in that case. Okay, and that does it for chapter 2. So make sure you're reading through, do the homework. If you're having questions, if you're having difficulty with any of the things that we talked about today, make sure that you're coming to my office hours and send me an email. I'm happy to get in touch with you as much as I can. You know, it's a little strange, you know, talking over videos this way, but I'm here to help, and just reach out if you need anything, okay? All right, well, with that, I'll see you soon. Bye-bye.